what is convergence in quadratic mean? What does quadratic mean? And now I'm using mean in two different ways. Miss McGillicuddy in 8th grade told you that the quadratic equation was y is equal to a plus bx plus cx squared. That's the quadratic equation thing. So whenever something is quadratic, it means it has square terms in it. And you know what the mean of the distribution is, right? How do you compute the mean of anything? Well, sample observation is. Add them up, and divide by the sample size. Just for the sake of argument, is there anything that says that I can't manipulate my observations before I divide by the sample size? I could square each observation and then divide by the sample. I could take each observation and measure it as a deviation from the sample mean and square each term and divide by the sample size. And that's an average, right? I might then ask, if I were doing that, all of those have quadratic terms in them, right? I'm squaring that. Suppose that's the sample variance, right? The sum of the squared deviations between the observations and the sample mean divided by the sample size. I could ask, suppose that we did it for many different sample sizes, and I arranged them in order by sample size. I could ask, what's happening to that sequence of sample variance? Right? Suppose that before I did that, suppose I figured out all those sequences, and before I put them in their respective barrels, I took the expected value. When I had sample size 5, I computed a sample variance and I put it in a barrel. And then I did have another barrel of sample size 10, and I computed all those sample variants. And I did that on and on and on. So I had a barrel a long way from here that had samples of large size, and I had a bunch of variances in there. And then I said, for the barrel of samples of size 10, I compute the average in there. And then I do the same thing for the barrel of samples of size 20, and so on and so forth. And on the outside of each barrel, I wrote the expected value of the random variables in the barrel from the outside of the barrel. So that when I got to the barrel a long way from here, in that barrel were a bunch of variances computed on the basis of samples of size 10,000 set. And on the basis of samples of size 10,000, I said, what's the average of those average squared deviations? And I wrote that on the outside of the barrel. And then I stood back and I looked at what I wrote on the outside of each barrel. And I said, what's happening to the sequence of expressions that I wrote on the outside of each barrel? And what I've done on each barrel is I've figured out the expected value of the sample statistic contingent on the sample size, and I wrote it on the outside of the barrel. And I did that all the way down the line. And I then asked, as I stand back and I look at what I've written on the outside of each barrel, what's happening to that sequence? Now, let me ask you, let's add a little more realism here. So, there's a barrel, and I have written, I wrote the sample size on the outside of the barrel. And in the barrel, I put s squared is equal to sum of the xi minus x bar squared over n, and then I wrote that. And it just so happens that the expected value of s squared, and by the way, that's the maximum likelihood estimator for the population variance. It just so happens that the expected value of that is n over n minus 1 times sigma squared. In this case, because n was 10 ninths. And I got a whole bunch of barrels. And in this barrel, where I have 10,000 in my sample, the expected value of s squared is 10,000 over 9,999 times sigma squared. Is this expected value closer to sigma squared than this one? Yeah. And if I kept going until I got all the way out here, in the limit, could you tell the difference between the expected value of s squared and sigma squared? Right. So the contents of those barrels is converging in quadratic mean for the population limit, like that explanation. So convergence in quadratic mean implies convergence in probability. Because in this example, what we have here, the variance is getting real small. And remember, we exploited the convergence of the sample variance on sigma squared and the convergence of the variance of the sample mean on 0 to prove consistent. So convergence in quadratic mean implies convergence in probability. And we expected that. We used that. Unknowingly, we used that theorem. Incidentally, how do you suppose, what tools that we have been talking about, how do you suppose that the people who developed the wall statistic, likelihood ratio, and Lagrange multiplier knew, and remember we said these were large sample tests, how do you suppose that the people who developed the wall statistic, the likelihood ratio statistic, and the Lagrange multiplier statistic all knew that they needed to read their critical values out of the chi-square table? What tools that we've been talking about, or one we use? It's for you. Yeah. What have we just been talking about? We We've just been talking about convergence properties. We've been talking about asymptotic. When you talk about large samples, you're talking about the asymptotic behavior of a random variable. And so the proof, in order to prove that those test statistics converge with chi-square, relies on one more piece, this notion of convergence in law or convergence in distribution. How many of you, as undergraduates, took a course in advanced calculus or real analysis? Anybody? So you've heard of the Stone-Weierstrass theorems. So what's the Stone-Weierstrass theorem? What does that say? Do you remember?
All I remember has to do with power six.
Stone and Weierstrass, together and separately, and their fellow mathematicians, argued that if you give me a function and tell me, and then I can construct another function to come within epsilon of the one that you have in mind. I can construct a polynomial of some degree so that over the entire domain of the function, I can get arbitrarily close to the one that you have in mind. And the way they proved that was to say, well, suppose that you have some exotic function in mind. It could be a gamma function, and we know what the gamma function looks like. Their argument is that I don't need to know the formula for the gamma function. All you do is draw it and tell me how close to it you want me to get. And I can find a polynomial of sufficiently high degree to get within epsilon of any point on that line. And so what they do is they construct a sequence of functions, where the sequence of function is identified by the power, the polynomial, the degree of the polynomial in the function. So f1 is just a first degree polynomial. It has x in. And that's not going to come very close to, say, the shape of a gamma. And they say, well, that one didn't work. So they try a second degree polynomial, and they see whether or not that one works. So given that you've told them how close you want to get over the domain, they can find a function of sufficiently high degree, a polynomial of sufficiently high degree, come within that distance of their functions they have in mind. So one could ask, what happens to the sequence of polynomials as the degree of the polynomial increases without limit? Well, it converges on this gamma. So that's the notion of functional convergence.